Welcome back, dear children. Now we will move to our next topic, that is the factors on which resistance offered by a conductor depends. So there are four factors on which resistance offered by a conductor depends. First one is the material of the wire. Okay, first one is the material. Now already we learned that we are having conductors and insulators, isn't it? When you take a conductor, it consists of more number of free electrons. That means the resistance offered will be less. Example, metals, isn't it? Then what about insulators or bad conductors? They are having less number of free electrons. So the resistance offered will be more, isn't it? So when you are considering the resistance offered by conductors, it will be less, and the resistance offered by the insulators or bad conductors will be more. So the first factor on which resistance depends is the material. That means if you are taking a conductor, then the resistance offered will be less. If you are taking an insulator, resistance offered will be more. Now we will move to the second factor, that is the length of the conductor. Resistance is directly proportional to the length of the conductor. So we already learned that the electrons will be moving from one end to the other end, isn't it? And what about the path of the electrons? Is it free? No, we are having positive ions. So when the electrons are drifting from one end of the conductor to the other end, they collide with these positive ions as well as on the walls of the container. So if length of the conductor increases, what happens to the number of collisions? Number of collisions also increases, isn't it? So the electrons have to complete more distance. That means more number of collisions will be there. As a result, what happens to the resistance? It increases. Now we will move to the third factor, that is area. Okay, area of the wire. Resistance is inversely proportional to the area of the conductor. That is, if area is more, resistance offered will be less. What is the reason? Area is more means the thickness or the width is more. So if the electrons can't move through one path, it can move to through the other path, isn't it? More space is there for the electrons to move. That means the number of collisions will be less if area is more. So what happens? The resistance will decrease. Okay. Now, when you are considering a wire, area is given by the equation pi r square. What is r? R stands for the radius of the wire. Okay. So in the case of area of a wire, it is pi r square, where r is the radius of the wire. Now, what happens if the radius of the wire is doubled? Okay. So if the radius is doubled, what happens to the area? Here we are taking r square, isn't it? That is squaring the radius. So if radius is doubled, naturally area will become 4 times, isn't it? Area increases 4 times. Why? Because we are not taking the radius, we are taking the square of the radius. So if the radius is doubled, area becomes 4 times. If area becomes or increases 4 times, what happens to the resistance? Resistance will become 1/4. Okay. So we have numericals related to this. So please keep this concept in your mind. Once again, when radius is doubled, area becomes 4 times. Okay. Area increases 4 times. So the resistance will decrease to 1/4 because resistance and area are inversely proportional. Now one more thing I can say. If radius is tripled, okay, if radius is tripled, what happens to area? Tripled means here it comes as 3r. So it becomes 3r whole squared means 9. 9 will come there, isn't it? So if radius is tripled, then area becomes 9 times. And so what happens to the resistance? Resistance decreases to 1 by 9th. Okay, so keep this concept in your mind. It will be more clear when we do the numericals. Okay, so resistance is inversely proportional to the area. Now the fourth one is the temperature. Okay, when temperature increases, resistance also increases. What is the reason? When temperature increases, the electrons will be getting more energy. So they will move more vigorously. So what happens? The number of collisions will increase, and as a result, the resistance also increases. Okay. An example what you can say is when you are considering a glowing bulb and a bulb which is not glowing. And in this case, which one will be having more resistance? More resistance will be there for the glowing bulb because there the temperature is more. When temperature is more, resistance will be more. Okay. So resistance offered by a glowing bulb will be more than the resistance offered by the bulb which is not glowing or which is in the off state. So is it clear? Once again, resistance offered by a conductor depends on 4 factors. First one is the material of the wire. It can be conductor or insulator. Conductor means more number of free electrons, resistance will be less. Insulator means less number of free electrons, so resistance will be more. Then it is directly proportional to the length. When length increases, resistance also increases because the electrons have to complete more distance, so more number of collisions. Then inversely proportional to the area. If area is more distance is there for the electrons to move. That means area increases, resistance decreases. And finally, it is about the temperature. When temperature increases, electrons are getting more energy. So what happens? They will move with more speed, more number of collisions. That means resistance also increases. Okay. So is it clear? Now, next we will be considering a VI graph. Okay. We are going to consider a VI graph for a conductor at 2 different temperatures. So VI graph, V is taken along the y-axis and I is taken along the x-axis. So we are going to consider VI graph for a conductor at 2 different temperatures, T1 and T2. T1 is greater than T2. So anyway, it obeys Ohm's law. That means our graph will be a straight line. Okay. So this much steep won't come. So this is the graph what we will be getting. Okay. We are considering VI graph for a conductor at 2 different temperatures, T1 and T2. Here T1 is greater than T2. Let this be A and this be B. And in this case, you can see that the plot or the graph A is steeper than B, isn't it? So why is A steeper than B? A means the conductor is placed at temperature T1 which is greater than T2. If temperature is more, what happens to the resistance? Resistance increases. And what is the relation connecting resistance and this graph? This is a VI graph. Slope of VI graph will give you what? It is equal to resistance, isn't it? Slope of a VI graph, V by I is resistance. Slope of a VI graph will give you the resistance. Now, T1 and T2, we are considering the same conductor at 2 different temperatures. T1 is greater than T2. So, the slope of the graph is more at greater temperature. The reason is when temperature increases, resistance increases. Okay. So is it clear? This question came once for the board exam. So the steeper one will be at a greater temperature. The reason is resistance increases with temperature. Okay. Now we will move to the next term. So we are learning many different terms in this section. Okay. So from the factors affecting resistance, we learned that R is directly proportional to the length and R is inversely proportional to the cross-sectional area. Isn't it? Now, I am going to combine these two. So what should I write? R is proportional to L by A. Isn't it? R is proportional to L, R is proportional to 1 by A. That means R is proportional to L by A. Now I am going to remove this proportionality sign. So this becomes R is equal to, if I put equal to, what is needed? We need a constant. Rho, okay, into L by A. This is read as rho and it is known as resistivity or specific resistance. Okay, it is called resistivity or specific resistance, rho. So is it clear? We got R proportional to L by A. I removed the proportionality sign and equal to is given. So I have to introduce a constant and that is rho or resistivity. Resistivity is also known as specific resistance. Now, how can we define resistivity? If length is 1 meter and area is 1 meter square, what will be R? R will be equal to rho, isn't it? And that is the definition for resistivity. Resistivity of a conductor is equal to the resistance when we are considering a conductor of unit length and unit cross-sectional area. Once again, resistivity is defined as the resistance of a conductor of unit length and unit cross-sectional area. If the length of a conductor is 1 meter and if the area is 1 meter square, naturally rho will be equal to R. Okay, so this is how we will define resistivity. Is it clear? Resistivity will be equal to the resistance if length and area are unity. Now, about the unit. So let me write the equation in terms of rho. So rho is equal to R into A by L, isn't it? R into A by L will be resistivity. What is the SI unit for resistance? Ohm. For area it is meter square and for length it is meter. This gets cancelled. So the unit is ohm meter. Okay. Ohm is the unit for resistance and ohm meter is the unit for resistivity. So is it clear about resistivity? Resistivity is equal to resistance of a conductor of unit length and unit cross-sectional area. Then its unit is ohm meter. Now we will consider the factors on which resistivity depends. Okay. Resistivity is actually the characteristic feature of the particular material. It won't depend on the size or shape of the material. In the case of resistance, we told that it depends on material length, temperature and area. But resistivity depends only on the material as well as temperature. Okay. Resistivity depends on two factors. First one is the material. If you are considering a conductor, its resistivity or specific resistance will be less. If you are considering an insulator, its resistivity will be more. Okay. So similar to resistance, it depends on the material of the wire. If it is a conductor, resistivity will be less. If it is an insulator, resistivity will be more. Now the second factor is about the temperature. Okay. Resistivity increases with increase in temperature in the case of conductors. So similar to resistance, when temperature increases, resistivity also increases, but it is only in the case of conductors. When you are considering semiconductors, do you know what are semiconductors? Semiconductors are substances whose conductivity lies between a conductor and an insulator. Okay, substances whose conductivity lies between a conductor and an insulator can be called as semiconductor. Example, germanium, silicon, etc. So, in the case of a semiconductor, resistivity decreases with increase in temperature. This question also came for the board exam once. Okay, so relation connecting resistivity and temperature. It is directly proportional in the case of conductors and it is inversely proportional in the case of semiconductors. So is it clear? Resistivity depends only on two factors. First one is material. Conductor means low. Resistivity will be less. Insulators means resistivity will be more. Then resistivity increases with temperature for conductors and decreases with temperature for insulators. Sorry, not insulators, semiconductors. In the case of insulators, anyway, resistance and resistivity will be more. Now, when we are considering the resistance, what was its reciprocal? Do you remember? Reciprocal of resistance. 1 by resistance was conductance. Conductance in your textbook, letter G is given. In few books, you can see the letter C. So, G or C represents the conductance. Okay. So, you use the notation given in your textbook itself. Reciprocal of resistance is conductance. Similarly, reciprocal of resistivity is known as conductivity. Okay. Reciprocal of resistivity 1 by rho is equal to what? Reciprocal of resistivity is conductivity. This is read as sigma. Okay. So sigma stands for conductivity. Is it clear? Then about the unit for conductivity. For conductance, resistance it was ohm. For conductance, what did we write? Ohm inverse or Siemens. Now, for resistivity, the unit was ohm meter. So, for conductivity, it will be ohm inverse or meter inverse. Or, one more unit we learned, isn't it? Siemens was there. So, Siemens meter inverse can be also used in order to write, can be also taken as the unit for conductivity. So, is it clear? Resistance is ohm. Conductance is reciprocal of resistance, so ohm inverse. Resistivity is ohm meter, so conductivity will be ohm inverse meter inverse. So is it clear? Now, few more things you have to consider related to this specific resistance or resistivity. Already I told you, resistivity or specific resistance won't depend on the size and shape of the material. Okay, so for a given conductor, if you change the length or area, it won't affect the resistivity. Only resistance will vary there. So few more things related to this change. Here we are doing numericals related to it, so it will be more clear. Anyway, I'll just give you what it is. Okay, so you're considering a conductor and suppose the length of the conductor is doubled. Our equation is R is equal to rho into L by A. For a given conductor, if a length is doubled by stretching, or a conductor ne valichu neeta, okay, so that its length gets doubled. If the length is doubled, what happens to its area? Area becomes half. Okay. So if the length of a conductor is doubled by stretching, its area becomes half. Then what happens to the resistance is it increases by 4 times. Okay. So we have numericals related to this. In a case where the length is doubled, naturally what happens? Its area will be halved. Okay, then what happens to the resistance? It becomes 4 times. Similarly, if the length is tripled here, the area becomes 1/3. Then the change in resistance will be 9 times. Okay. So once again, if the length of a conductor is doubled, area becomes half, and then the resistance increases 4 times. So keep one point in your mind. Okay. Then with that we can do all the other things. So is it clear? Then one more part is given about the change in length. So when we do the numericals, I'll make it clear. Now you please keep this concept in your mind. What is that? When length is doubled, area becomes halved, and then resistance becomes 4 times. Okay. Now we will move to the next part, that is about the choice of material of wire. So we are using different wires, and on the basis of specific resistance or resistivity, we are actually choosing the type of wire. First one is in the case of transmission lines. So in the case of power transmission lines, the power is transmitted to a greater distance. That means energy loss should be reduced. So normally for power transmission cables, we will be using wires which offer less resistance to the flow of current. So which are the substances which offer less resistance? In general, metals, isn't it? So normally copper or aluminium is used in power transmission lines. The reason is they are having low resistivity. Okay, the specific resistance or resistivity is less when you are considering good conductors such as copper, aluminium, etc. Actually, silver is the best conductor, but due to its cost, we won't use silver lines. We will be using copper or aluminium. Okay. Now the next thing is to make the resistors. So in order to make the standard resistors, we need elements with high resistivity, isn't it? So alloy of constantan or manganese is used in order to make standard resistors. Now the third one, in the case of fuse wire. So we'll be learning in detail about fuse in the next chapter. Okay. So in the case of fuse wire, we will be using an alloy of lead and tin. The reason is it should have low melting point and high resistance. It should not allow much current to enter into the house. So low melting point and high specific resistance is needed for a wire which is used as a fuse wire. Now the next thing is in the case of a filament bulbs. The filament, it is made up of tungsten, because a filament bulb will emit light only once it gets heated up. The filament bulb means the earlier days we were using the bulb which gives yellow color light. So it should get heated first, then only it will be emitting the light. So in the case of filament bulb, what about the specialty? What type of element we need? Here the filament, tungsten is generally used as the filament, and in the case of in the case of filament bulb, it should have high melting point. If the melting point is less, means it will melt and the bulb gets fused. Okay. So high melting point is needed there. And the next one is in the case of heating appliances such as oven, heater, etc. There normally we will be using nichrome. The reason is nichrome offers high resistance. So if the resistance or the resistivity is more, means what happens? The heating effect produced will be more. So this choice of wire is also important. Okay, once or twice questions came from that. Once again, in the case of power transmission lines, we are using copper or aluminium. The reason is it has low resistivity. Then the next one is in the case of standard resistors. We will be using substances with high specific resistance. There, alloy of constantan or manganese. Then fuse wire, alloy of lead and tin, low melting point and high resistance or resistivity. Then filament bulb, tungsten, because it has high melting point. Then for heating appliances, tungsten, since it has high specific resistance. Now, one more point is there, the last topic in this section, that is about superconductors. Okay, so do you know what are superconductors? When you are cooling certain elements to a temperature, very low temperature, it offers low resistance to the flow of current. Such substances can be called as superconductors. Okay, so what are superconductors? Substances which offers zero resistance to the flow of current at low temperature, at very low temperature. Normally, in the case of conductor itself, it offers certain resistance to the flow of current, isn't it? But when you are cooling certain substances to a very low temperature, what happens is it offers zero resistance. Even though there is no potential difference, current flow continues. Okay. And such substances can be called as superconductors. Example, when you are cooling mercury to a temperature of 4.2 Kelvin, it offers zero resistance to the flow of current. So is it clear? Few examples are given. Study at least 1 or 2 examples for superconductors. That is, substances which allows zero resistance to the flow of current at very low temperature. Okay. So with this, we completed the section. Then in the last class, we completed till question number 14, isn't it? Now, you can start with question number 15. Question number 15 to 34. If the answer is there, no need to copy it into your book. If the answer is not there, you have to write the answer. Since many questions are there, no need to copy the question. Just read the question, find the answer and write it. Okay. So, please study the portion. Many new points are coming. Be thorough with this. Okay, children. Thank you.